Hello everyone. We've basically already covered this in a previous video. The main difference with what we're doing in this unit is largely better notation. We don't have to read a whole question to figure out what we need to do next. We know at a glance if it's a particular interval, also known as a definite integral, or not, which is known as an indefinite integral. We also know what variable or variables we need to be worried about, which will be very helpful one day for us all with multivariable calculus. If your definite integral goes to infinity in either or both directions, which do exist, then it's called an infinigral. It isn't really, but it should be. So we're going to leave all this behind for the most part and focus on the stuff in this box. So if f is a continuous function on an interval from a to b, then the integral of the function from a to b is the antiderivative of f at b minus the antiderivative of f at a. And now we have some better notation for this. So we're going to do this first one together. So we're integrating x cubed from -2 to 4. So we need to first ask ourselves, where did this derivative come from? Well, it came from x to the 4th divided by 4. And using our new notation, we're going to go from -2 to 4. Next, what we're going to do is just sub in 4 for x, 4 to the 4 divided by 4. And then we sub in -2 to the 4th divided by 4, which is 64 minus 4, which gives us 60. Notice I didn't include a constant here because it's not really necessary with definite integrals. So the way we can interpret this area, it turns out that this particular area is positive 64 and this area is -4. So I have something for this. I've posted this link in the description. It's a very basic integration visualizer. You can think of this as sort of a jumping off point. We have a function here, the integral from a to b. You can adjust the intervals from a to b, and there's some optional extras in here, giving lines and shaded regions. So hopefully you find this somewhat helpful in the questions ahead. I'm going to leave part B for you to do. I'm going to leave it to you to prove that the result is -4.5. I'll give you one hint though. It would be helpful to expand and simplify this before you integrate it. Question number 2a, I'm going to leave for you to do as well. So my hint for you on this one, this function is equivalent to t squared over t plus root t over t minus 2 over t. And I'll leave it to you to confirm that the result is 19/2 minus ln of 16. I'm going to leave part B for you to do as well, because these are actually kind of fun, and it's good for you to get some practice. So I'm going to leave it to you to confirm that this result is 1, and my hint for you on this one is to check your antiderivative is correct by applying the chain rule. Part C we're actually going to do together because it's relevant to our next class. I'm just going to leave you with one question here. Would you rather do this integral or this one that I'm about to write? Which one looks simpler? So we need to figure out where this derivative came from. It may help for you to write this as 1 over x squared plus 9 times 6x. There's bound to be a natural log in here somewhere because we have 1 over something. So we could maybe try ln of x squared. The derivative of this would be 1 over x squared times 2x, which is kind of in the neighborhood of what we need. If we tried ln of x squared plus 9, the derivative of that would be 1 over x squared plus 9 times 2x, which is a bit closer, and if we multiplied that by 3, we'd actually have what we need. So if we multiply this by 3, and the same thing for the right side, that's what we get. So the next step with this integral is we should write 3 ln x squared plus 9 on the interval from 1 to 4, and now we can just sub in 4 and 1 into this function. So first we can go 3 times ln of 4 squared plus 9, and 4 squared is 16, plus 9 makes 25, so we would have ln of 25 minus ln of 1 squared plus 9, which is ln 10. We can use our log laws to simplify this expression, so we get 3 ln 25 over 10. And 25 over 10 we can simplify a little bit. We can make that 5 over 2. And furthermore, we can use another log property and write this as an exponent, ln 5 over 2 cubed, which would finally be ln of 125 over 8. And that's our final answer. Part D I'm going to leave up to you to do as well. We've actually done a similar antiderivative in area under a curve and antiderivatives notes from last unit. I'm going to leave it to you to prove that this result is 1/4. So that's it for me for today. I'll see you next time.